So we are talking about the Ethereum 2.0 spec, and this talk is about the protocol specification about the beacon operation. We saw in the last weeks things about the beacon state, and now we are talking about the beacon operations. So let's move. We are talking about the phase 0, about the beacon chain. Remember that this kind of protocol specification is divided in different phases, and you have here the phase 0 and also the phase 1 and also the phase 2. So right now the phase 0 is how this beacon chain starts. Let's summary the simulation of this kind of protocol. So right now this is boogie simulation about the protocol specification. So it's here the Genesis state with the beacon chain in Dogger blue blocks in the center, and the shard chains Aquamarine positioned in a circle with a beacon chain in the center. So the Genesis state start. The crosslinks start, that will be the blue arrows between beacon chain and the shard chain, and there is the first crosslink, and this crosslink it's under the hood the number of attestations, and attestation it's thing that connect beacon state with the shard chains for the longest chain rule and has a better performance in the data. So sharding is actually an experimental thing right now in the protocol specification of Ethereum. So let's move to see this attestation thing under the hood for understand in Python what it's all about. So we have here the beacon operation. So we have a different beacon operation that this beacon chain has. So this beacon block have this operation, the proposal slashing, the attestation slashing, and the attestation. So far the proper slashing is a condition that the block accept or reject different things for reach the consensus. And this attestation slashing, it's a thing that decide this is a good attestation or this is not a good attestation. So it is not a good attestation, you are slashing that. So it's like I don't want that. So it's, but in order they could have an algorithm for this condition, no? Isn't? So let's move to the attestation to understand. So we have here the attestation code. So far the attestation it's a thing. I have aggregation bits, have the data, that is the attestation data, and the condition of the signature, that in this time it's a VLS signature, and this VLC signature it's kind of signature that this Ethereum 2.0 wants to develop. So far this VLC signature are so hard for understand, and we saw in another videos basic things about VLC signature because are so extend and have a lot of abstraction things that we'll see in summary. So let's move to the code to see things about this attestation. So first let's to find all the things about the attestation. So just do magic copy and paste. So let's check. And the data start. So attestation it's everywhere. And you have a lot of things in the attestation, in the chain side, in the exception side, in the schema side, in the LMD goals, that is the algorithm for the Ethereum 2.0 implementation. That also is called Casper FGG. So let's move to see the first attestation. So you can see that it's everywhere. this attestation thing. Okay, so you also have attestation in the node, the chain, validator, IP, validator. So let's move to see only in the beacon because it's the phase 0. So if you see something in the validator side or maybe in the shard chains because it's the phase 2. So I think the best option here is only see here in this beacon because it's the Genesis state for understand under the hood the protocol. And so far you have here the simulation that this Genesis state is the first block in the beacon state, and then you have different shard chains positioned in a circle. So let's move to see only in the beacon state because it's only the phase 0. So you have here a folder in the open source that the Ethereum Foundation share with a license in MIT. So it's a good thing for understand Python and also BFT protocols. So let's move to see. You have different folders, so that is the different implementation in different protocols. For example, implementation in the Byzantine fault tolerance protocol. It's called in A2 version 2. You have the implementation in the peer-to-peer implementation that it's a network. So you have here. You have the scripts for debugging all the things, the folders of tests, something properties of cached and so far things that you need to debug here, and also documentation, something that is automatic build when you make a heat hub, documentation, scripts, and so far. So this protocol specification have this folder, and you can find here the beacon chain that it's all about this principal chain that have a governance with the shard chains and also all the language chain. Remember that in this kind of leader-based Byzantine fault tolerance protocol, the longest chain is the principal rule for this consensus. So let's move to see this attestation helper, and let's replicate this code for understand how to validate in this beacon state the attestation. So let's move here and zoom in this for a better okay. So start with the first function here that will be decorator that validate index attestation aggregate signature. So you have here a state of this. The state of this is the beacon state. So the beacon state is an indexed attestation. So this indexed attestation have something that it's have a parameter for this condition. So it's the slot per epoch condition. So this object will be unknown. You have attesting indices in the sec attestation. So the attestation indices need the pub key of the VLS signature, that it's only a cryptographic digital threshold. So these aggregate put keys will be tuple condition, and this tuple condition is a state of validator condition. So put key for E in attestation indices. So let's see this attestation thing in pseudocode for understand better. So you can find this. Let's see timeline of VFT protocol and see the station thing in another kind of algorithm, but in the same related world of PFT protocols. So this is timeline of this. Let's see timeline of it. See the station thing in another kind of algorithm, but in the same. So you have here this timeline. So the attestation meaning you can find here in this kind of protocol that is calling, can't remember very good. Okay, it's the small trusted hardware for large distributed system. So let's see this. So let's see this paper for understand this. So this paper was writing in a time ago by Microsoft researchers, and they use this attestation team for have a better development in a VFT protocol specification. And this attestation, it's a kind of membership thing. So this paper showed that this implementation is practical, versatile, and easily applicable to wide range distributed systems. So this implementation, it's a case of studio in attested append-only memory. So this attested is for the election of the memory that have this kind of implementation, and it's very similar for the BitTorrent implementation. So you can find here the algorithm of attestation. So it's the generative attestation. So the core of this implementation have this interface that have this attestation thing. So the attestation takes the parameters. Here EA, it's the identity for a counter to use C. It requests new value for that counter, and H is a hash of the message M to which the user wishes to bind the counter value. The state works as follow, and you can find here the first algorithm for attestate. And this is a kind of primitive for the attestation that the Ethereum 2.0 use, only that you change different variants here, different variables, the context that you have becomes chain, that you have another chain that is called in the Ethereum 2.0 that is a proof of work chain, and you are getting this data in this beacon state, and then this beacon state needs to make different things in the other shard chains. So let's move to C. So you have here this algorithm, and the algorithm is the first line of this algorithm is that assert module that is the identity of a valid counter. So then when you have assert this, let C be the value of that counter and key be the key. So it's a model that have the PKA stuff for having a better performance in the cryptographic way. So then assert not roll it over, you need to have this condition that C it's less than the derivation of this C. So the next condition is a statement. So if K it's not 0, then let A get all this data. So this is the key feature of this attestating, that you need to have this condition for the thing that you need for pass to another state, have the thing that you need. So you can imagination here that the beacon state needs another thing for finalize the next block. So this is the variant that the beacon state has. So this part is when A have all this, and otherwise let A have all this, but with all the key private key. So insert A into Q, kicking all these values. So you debugging very nice with this attestate thing. So you update your new state and return all the thing that you don't need for the next state. So this attestation is the thing that the beacon state use for having all the things that the next block needs. So the crosslinks it's the way for validate the beacon chain and also the shard chain. So when the attestation is good for the beacon state, the number attestation start with this crosslink that validate two different kind of state. So it's a good way for having this. So let's move to see more code. So let's zoom this. I always forget my command line. So you have here this validate indexed attestation. So let's move to see what more things needs for make this attestation successful. So the message that it's an indexed attestation is a data have the hash 3 root, the domain, get the domain. So you can see that start to make the things that the algorithm do, but in different variant. I mean, you need to get all these things, but it's only for update another state in this algorithm that attestate all this thing that it's the input that it's parameterizer for the attestation thing. So it's a very good for CDs. So get this domain you have the state, the signature. Remember that you need to have signatures everywhere for make a secure protocol. So we can attest there that it's the instance that make this attestation thing. So a slot per epoch, the indexed attestation data as a target epoch. And remember that the epoch and all the slot per epoch is the thing that need the attestation for make this cross-link thing for having a connection between the beacon chain and also the shard chain. So you can see that all these inputs here is this kind of primitive in the attestation mode. So it's all this input. So this BLS signature, it's a validated state. So the pub key is equals to the pub key, the message hash is equals to the message hash, the signature it's equals to index set attestation signature, and the domain it's equals to the domain. So you can see that the input here have this attestation for validated state. So it's a tricky part for this kind of attestation, but you have to aggregate the signatures in the BLS way. That it's the new way that the Ethereum 2.0 wants to protect cryptographic all the network and all the consensus meaning. So let's create this new div validate indexed attestation. So this validate attestation also needs the state. Remember, it's the beacon state. You also have the indexed attestation. That's indexed attestation also. So we need to put all these input also that you also have in the algorithm here. So it's a very good way for the book this thing. So it's only a variant of this. So you have this. So the max validator, remember that you need to sync all and also you need to validate all. So the validators per commit is an int, and the slot per epoch, that is the way to connect the beacon state with the shard chains, will be an int. The validate signature is boolean, that it's a true. So this known. So this is when the algorithm start for having the input that you need for make this attestation thing. So there is a lot of conditions. So the attestating indices will be the index set attestation with the attesting indices. So you need to start thinking in the statement. So if the length of the attestation, the attestating indices, it's more of this condition. When this happen, the algorithm start make this magic thing here of having the private key of the way that you want and insert all the A into a new state. So this condition happens, so trace a validation error for debugging this, and you have different conditions here. So if the list of this attestation indices is not equal to the sorted, the set attesting indices needs to rise the same. Validation error. So you see the way of the list. That, remember, we are here in Python, so you need to put all this in a list because everything here is an object. Then the length of the attestation indices, that's a kind of helper. So then you need to make the other side of the validate signature. So if the validate signature try validate indices attestation aggregate signature, you have the state, the index set attestation, slots per epoch. So this is save signature error as error, raise another condition here. And you have here this decorator of the validate index attestation. That it's only this algorithm here. Then you need to insert A into Q, kicking all this value. And you have more things here for this kind of development thing. So let's move to C in the slashable attestation. So remember, the slashing condition is a thing that slashable attestation data. So the data one have this attestation data, so you need to put all the data here for make. So this will be a predicative. So you need the boolean function here for checking double vote or surround vote. So return the data one of this condition. So it's not equal to data 2. And the data 1 target epoch data 2 target epoch. So in this way you check if data 1 and data 2 are slashing according to the Casper protocol specification. So you read this, so you make this slashable condition. So it's a way for debug this, but in the high level of the state of the art. And the state of the art is that you have a PF2 protocol that needs to reach a consensus, and you also have the consensus rules that it's maybe the two and 3/4 of the protocols needs to be honest for having a good state of the art of the consensus protocol. And this state of the art is also a mechanism. So this slashable attestation data, it's a condition for having another way for reach the consensus and have extra security in some sense. So you have this data epoch. Remember that epoch is the way for the beacon state have this connection. So the data 2 is a source epoch and data 2 is a target epoch less than the data 1 target. So you finalize this slasher attestation data. So you have here this attestation helper for make this attestation thing for put A into a queue, kicking out all the things that they have. So it's a interesting way for pass one state to another state. So let's see more about this attestation. So let's see in the code more things about this attestation. So you have here the same attestation helper. So let's see the other side, the epoch processing helper. So let's make this. That will be the epoch processing helper. So you have here, so diff increase balance. So remember, it's all about the state. That's the beacon state. So the index validator index, you have always these constants in the protocol specification. That is the way, that is the thing that also have for execute contracts, smart contract that they are sub-protocols of the implementation. So the beacon state return the state of transform balances and the index. So you need to think in all the balance that you have in this increased balance. So you are seeing here the epoch processing helpers that you need to import the block root, you need to import the block root and the slot, you need to import all the total balance. So this kind of utilities will be a tuple in the way for have the iterable thing, the sequence thing, then you have the set, and you then have the tuple thing. So it's a thing for you. So you have different things here for the protocol specification and decrease balances. So if you want to decrease the balances, so let me see this. So far, for example, in this design that they do in this hardware large distributed systems, they do this attestation for different design walls, and the fundamental security of this implementation is to remove participants' ability to equivocate. So the attestation in under the hood it's also this design wall. So you need to remove adversaries of this protocol specification. So this increased balance and this decreased balance, it's for getting this attestation in the better way. So it's incredible how to design this wall in the Ethereum 2.0 config. So this analysis of this data could you help for make a VST protocol from the scratch and have a better understand of how to use this kind of implementation in another things. So let's see this decrease balances. That is, you only have this diagram of them. You have the part that you need to increase, and you also need the decrease balance. And remember that it's the design will forbid all the adversaries of the state of the art. So you also have the same, so you only make the copy paste magic because it's the same thing. So the beacon state need to return the state of transform this, and it's all about the balances. And remember that you have your funds in a one address, and this address is not the unspent transaction, the UTOX model. So you need to do this because you have different tokens here. You have more data. I don't know, a lot of things here. I mean, so the way that is the thing that needs the contract for execute the worst day of the Ethereum virtual machines. So if this condition of delta it's else the way, balance plus delta. So let's start to think in these get attestation indices. Remember that in the algorithm they use one thing that needs to pass the thing that this thing have, and then put in another state. So this get attesting indices will be the beacon state, and this attestation data will be the attestation data of the field. It's calling the bit field here, that it's a protocol specification for handle better this, and the config is the A2 config. Then you need to set the validator index. Remember that you need to sing all and you need to validate all. So the commit will be get a beacon commit of the state. So this is the part when you connect the beacon state with the shard chain in the phase 0. I mean, you need to make this attestation thing, forget the beacon commits. So it's all about the attestation data. So the target of this is the slot, and the attestation data is an index config. Then you need to return the set that you do. So you have the index for the condition so if this condition has voted of the bit field, you have a successful attestation indices. So this is the part of these attestation indices that under the hood it's only the part for remote participants' ability to equivocate. Consider the situation wishes to send conflict messages to Alice and Bob. So you are only debugging these conflict messages between the part 8 and the part B. Common approaches to combating such equivocation require to communicate with one another or with a third part, so they can learn for the distinct messages sent to edge. So it's a very good design wall of the attestation thing in the PFT protocol, that is the Byzantine fault tolerance protocol. So let's see. So in this part you have the state of the beacon state, that is attestation, that is equals to the attestation, the config, that is this config. So the index set attestation. So in this part, we're talking about the phase 0. So you have here the Casper FSG, that is the algorithm for that is friendly ghost, that's is calling Casper, is making this attestation in the way that they want to connect the beacon chain and all with the shard chain for make this a consensus rule that is calling the longest chain to reach the consensus. and have a consistency network and have a liveness network. That are the two kind of constants that the BFT protocol has. And also remember that the three main ingredients for BFT protocol is the validation meaning. Also, you have the terminated meaning, and also have the other condition that is reach the consensus. So these three main ingredients, it's very particular for the state of the BFT protocol implementation. So let's see more this thing about the attestation meaning. So get attestation indices will be a state attestation data attestation aggregation bits. You can find here this all in the protocol specification here. You can hear that the attestation is three main ingredients under the hood in the code for these aggregation bits. That it's the list of the maximum validator per commit. That it's the constant of validate all the commits that you need to do for the share chain. And also you have the data of this attestation data and also the signature. So this protocol specification is that thing. So in the point of code, you need to make all this code in this way. So this attestation aggregation bits. So needs the config of the A2 config. So you need return all this index set attestation, create the attesting indices, so the data of attestation data need to signature in the model of the BLS signatures. So this extension of this model is very interesting in this finality gadget. So I have this problem here. So far you have this get at attestation indices, and you have the indexsec attestation. That are the two kinds of way for having the set validation index, for have the beacon commit and pass to the next state that it's calling the sharp chains. So you have here this Ethereum 2.0. This is a buggy simulation, but help a lot for have a better imagination of this. So the code that we are doing here or trying to analyze, it's when the attestation that also it's this kind of lines start to make all this get beacon commit. So it's one in the time, no, in a cycle, in a round thing. So the code that we are writing right now is that way, no, isn't it? That you have here. So let's move to C. So my time is over for now. In the next video, tomorrow, the same the same time. We'll see different things about this attestation for matching the attestation, target and the heat, and also the slashing condition of these attestation indices, get the attestation balances, and also the crypto economics thing have this phase reward. That's interesting way. So this attestation is in all the protocols for the side of the validation side, also for the beacon chain side, for the shard chain side. So it's a key feature for reach the consensus in a safety way in this incredible protocol that it's amazing figuring out how to build this kind of things. It's incredible. So see you in the next video for see this kind of station things.